Good day, everyone. Today we will be discussing terephthalic acid, including its overview, reaction mechanism, and the chemical tests associated with it.
Terephthalic acid is a primary raw material used in synthesizing polyethylene terephthalate plastics and polyester fibers. It has an approximate melting point of 300 degrees Celsius and a boiling point of around 392.4 degrees Celsius, where it sublimates and decomposes before reaching a true boiling point. It is poorly soluble in water due to its rigid aromatic ring structure, which limits hydrogen bonding with water molecules. Now, it dissolves more readily in alkaline solutions and in organic solvents such as dimethylformamide and N-methyl-2-pyrrolidone, where it forms soluble salts.
The conversion of benzene to p undergoes a series of Friedel-Crafts alkylation reactions that use methyl chloride and aluminum chloride as key reagents and catalysts. The reaction begins with the formation of an active electrophile where aluminum chloride, acting as a Lewis acid, reacts with methyl chloride and attracts the chloride ion. This interaction breaks the carbon-chlorine bond and generates a methyl carbocation, which serves as the reactive electrophile. In the first alkylation step, benzene acts as a nucleophile. Its pi electron attack the methyl carbocation to form a temporary sigma complex, which briefly disrupts aromaticity. When the proton is released, aromaticity is restored, forming toluene as the product. In the second alkylation, the methyl group on toluene activates the ring, directing substitution to the orthone para position. Another methyl carbocation attacks the ring, producing p-silane and O-silane, with p-silane as the major product because of its less steric hindrance at the para position. Afterward, p-silane is isolated from O-silane through fractional crystallization. The silane mixture is cooled in an ice bath and stirred slowly. Because p-silane has a higher freezing point, it crystallizes first, while O-silane remains liquid. The p-silane crystals are then collected and further purified by dissolving them in a hot hexane and cooling again to recrystallize. Finally, the crystallized are washed with cold hexane and allowed to reach room temperature to obtain pure liquid p-silane.
In the conversion of p-silene to terephthalic acid via ozonolysis, a mixture of p-silene, acetonitrile, and water under basic conditions is placed in a reaction vessel in a dark room at room temperature and 1 atmosphere. The acetonitrile water co-solvent improves the solubility of otherwise insoluble reaction intermediates. Dilute ozone is then introduced by bubbling it into the mixture. The mixture is then photoirradiated with a 100-watt Hg lamp as the UV source. The ozonolysis proceeds until a white precipitate forms, which is filtered and collected as crude terephthalic acid. The process begins with hydroxyl radical formation. UV light decomposes ozone into molecular oxygen and an oxygen radical. The oxygen radical then reacts with water to produce two hydroxyl radicals that will initiate the radical reaction in step 2. In the second step, the hydroxyl radical abstracts a hydrogen from an alkyl group of p-silene, forming an alkyl radical in water. The alkyl radical then reacts with molecular oxygen to yield an alkyl peroxy radical, which then abstracts a hydrogen from another p-silene molecule, producing a new alkyl radical and a hydroperoxide group. Under UV light and basic conditions, the hydroperoxide's weak oxygen-oxygen bond undergoes homolytic cleavage, rearranging into an aldehyde because the formation of the carbonyl is more thermodynamically stable. Water is also produced in this step. Afterwards, the 4-methyl benzaldehyde intermediate is then oxidized by ozone, which attacks the electrophilic carbon, forming 4-methyl benzoic acid and releasing molecular oxygen. In the final step, the other methyl group of the 4-methyl benzoic acid intermediate first undergoes hydroxyl radical initiation, then reacts with molecular oxygen to form an aldehyde substituent and is then oxidized to a carboxyl group by ozone, yielding terephthalic acid as the final product.
In the case of the terephthalic acid, it actually contains two carboxylic groups that can undergo esterification. However, under normal lab tests, the reaction is very slow or might not occur at all because the two carboxylate group is directly attached to the benzene group, making them less reactive, and the compound is not very soluble in alcohol. So, when we perform these tests using the ethanol and then the concentrated sulfuric acid, we don't observe the typical fruity odor, meaning the result is negative. However, in industrial processes, where high temperature and catalysts are used, the terephthalic acid can react to form dimethyl terephthalate through Fischer esterification.
Another test that can be used to characterize terephthalic acid is the sodium bicarbonate test. This test detects the carboxylic acid groups present in a compound. Its main focus is the reaction between the acid and the sodium bicarbonate, where the acid donates a proton to the bicarbonate ion. This produces carbon dioxide gas, water, and a salt as shown in the reaction equation. The formation of bubbles indicates the release of carbon dioxide gas, a positive result confirming the presence of carboxylic acid groups. Therefore, we can conclude that the compound tested is terephthalic acid which contains these groups. As a safety reminder, perform this test in a well-ventilated area and wear proper protective gear since carbon dioxide gas is produced.